my screen? No, not yet. Now, perfect. Can you see my screen?
Yes.
Okay. I take 5 minutes. So I teach at the Vienna University of Technology. Today, all of you meet the students from our design studio. The Vienna University of Technology is a very big university. We have 14,000 students, 6,000 architecture students. So I think with the TU Delft, we are the biggest architecture faculties in Europe. We offer a regular space architecture program. You can find most of the publications online. This is the link if you're interested. We did some studios related to the moon and to the Mars, but also to space. I work at the Department for Construction and Building. So as a tradition, we build a lot. We work a lot with physical models normally, and the students have to work on a concept first, and then they have to go quite far in their detailing. Here is, for example, we did a one-to-one workshop with the Austrian Space Forum. This was a Mars deployable shelter that was then tested in the desert in Morocco. So 5 students had the possibility to go there and test the mission with the spacesuits. And my background is I'm an architect, so I built interior projects and small compact buildings on Earth. And my research is related to architecture. In space, Henriette, we talked about the book, my first book, which was the outcome of my thesis with Richard Horden, who was a specialist in microarchitecture, you might know. Unfortunately, he's not with us anymore, but his books are very, very good if you want to have a look. My thesis was an analysis of all spacecraft built and inhabited from the point of human activity. So sleep, hygiene, food, and I analyzed them according to architectural parameters, kind of flexibility or volume and usability by the astronauts. I also interviewed some astronauts like Rubu Okis on that. What I did with Olga Banova is the director of the 6 of the Sussex Harbour Center of Space Architecture in Houston. You might know her. If not, the publications from them are also very interesting. They mainly teach engineering students there and have only a few architecture students. Both of these books you can also find online or as a PDF. My students have an email link, a link if you're interested. And this semester we decided to work on the Mars Science City. And I have to say, originally the idea was to work more closely with the UAE, but but due to the circumstances, we had to change the plan a little bit. Originally, we wanted to plan the Mars Science City in the desert in Dubai as a simulation facility for Mars missions. But now the students and myself, we have decided that we will stay on Mars, and they are all planning Mars habitats. It happened because they were so eager. They all wanted to plan on Mars. So they were a bit sad when I told them they had to plan on Earth. So we decided to plan this on Mars. Today you will see 2 projects of mine, and thank you for joining us, all of you. Great to see you.
Yes, thank you, Sandra. Sandra?
Yes, I'm here.
Okay. Should I take over, and after me, Advenit or?
Yes, please. Yes, please.
Okay. I share my screen. I think you have to allow me to share it. Or not? Yes, I can. Do you see my screen?
Yeah, yes, we can.
Okay. So let me just make this small. So I'm going to introduce our project that the students work on, a rhizomatic habitat on Mars. I have to say that this is actually the first project. So all technology that we are proposing, we tested on Earth, and I'm going to introduce that a little bit. I have a problem now with my presentation. For some reason is...
Just press enter because you have a... Sorry, this is my screen, I'm sorry.
Yeah, now it's frozen somehow. Okay, let me try here. Yeah, okay. So this was our submission for the first and is organized by European Space Agency. And actually we entered with a group of students and researchers this phase who were interested in developing a habitat for Mars. So our proposal was to build below ground. And the idea was to deploy a swarm of rovers developed at architectural engineering in TU Delft. And these were deployed to excavate into the ground in a downwards spiral movement. Subsequently, the created cavity is reinforced with Martian concrete, which is a mixture of regolith and sulfuric acid. And when the first tunnel, so to say, arrives the depth that is below ground that is supposed to achieve, the rover starts to move upwards in a spiral movement. And with that, basically, we create a space that is strong enough structurally so that we can excavate the in the middle all ground, and we can place an inflatable unit for the life support system. So as mentioned before, we would use technology that we have been developing at TU Delft, amongst others also kite power. So we use kites to generate energy for excavating and also for having the habitat inhabitable. So in terms of technology, we proposed to use subtractive and additive manufacturing that we have been developing in the last 6 years. So this technology or methodology that we have been developing, and both actually, we call designed robotic production, assembly and operation. So I'm just going to give you 2 examples so that you, or 3, so that you have an idea of what this implies. So we have a system with a robotic arm, and we connect the robotic arm to a computational model. And we also connect the arm to end effectors that we are customizing. In this case, we had an end effector for 3D printing with ceramic clay. So this project with ceramic clay has been exhibited at Centre Pompidou And it started with an overall design, a pavilion, as you can see. And we translated the computational model into a robotic path. In this case, the end effector was a light. In a second step, we experimented with clay. In this case, we deposited clay on a double curved surface. This was just a test. The actual exercise was focusing then on taking a fragment of the overall geometry, structurally optimizing it so that we could create a cellular structure and reduce material use and also increase production speed. So here you see the cellular structure that we created. And the idea was that now this cellular structure needs to be translated into a continuous robotic path, which we did. And this was actually the final prototype, a fragment. So we usually always work with the fragment that we are prototyping, an overall design, but also a fragment that we are testing. So here you see another project with a similar logic where we used recyclable plastic in order to create a chaise longue that has variable stiffness. We again implemented structural optimization and then also this cellular material design, which allowed this behaviors, which means the back was reclining, is able to recline to a certain degree. So this idea of designing not only, let's say, buildings or artifacts, but also designing the material, we find quite fascinating. So we have been also using subtractive techniques in this case to make from a material that is not flexible, a material that has some level of flexibility. And in principle, we have been working with various materials until now, such as EPS, wood, ceramic, clay, plastic, etc., silicon as well. And last but not least, we looked also into assembly. So we tried to identify all areas that are required in architecture and test their potential in architecture. So in this case, we looked into stacking of elements, of linear elements of various sizes. And the challenge in this case, amongst others, was to create a structure that was stable from the first moment until it was completed. I'm not going to show this all the way to the end because I guess everybody got the picture. I would rather move to the next slide, which is this one. So what we understand is, of course, that human and robots work next to each other. The environment needs to be safe, and there's some level of collaboration that we would like to and are interested in developing, which we are going to do with Delft Robotics Institute in the next phase. With this, actually, I would like to conclude my presentation. So there are going to be 3 students presenting their group work, and 2 of the projects are going to be not only the group work, but basically they have been developed further with our main competition team. And this is what they are going to present next. So Sandra, I finish now. I guess Advenit could present.
Yeah, yes, I can say a few words about what we do. Let me see. Where is the share screen? I will share. Number 2. Let me know if you see my screen.
Yes, we see it.
Okay, so just a few words about what we do. I'll try to keep it short. The presentation is long. It was for a workshop, but I'll make it quick. So yeah, just a few words about ESA, 22 member states. We are active in pretty much every area of space activities: human space flight, robotic exploration, science, Earth observation, telecommunications, and so on. So in the past few years, there has been a renewed interest for human and robotic exploration beyond LEO. For one, because the International Space Station is expected to end its current life. We're talking about commercialization later on, but the purpose of the ISS for exploration will stop at some point. So we are looking beyond. With ESA, it means collaboration, international collaboration for mission to the moon and to Mars. The private sector is also very active, what we call new space, with SpaceX Blue Origin being an example. And we see more and more new countries coming into space activities, China, India, to name a few. So I will talk about what we have been doing in the agency, in particular in my materials and processes section, to which I belong, on additive manufacturing for exploration in orbit and on planet. So additive manufacturing on orbit, the motivations are to revise the mission logistics. So during long duration exploration mission to Mars or long duration mission around the moon, you will benefit from the on-demand production capability for spare parts, tools, etc. A few examples of what we have done. So the Italian Space Agency flew a polymer printer in 2015 on the ISS, operated by Samantha Cristoforetti. The material was PLA, so not the best material, but was a good demonstration. And we have, after that, been working on a polymer printer for engineering polymers, PEEK, for higher strength. So the type of polymer you can really be using for tools and spare parts. And this printer can print independent of the gravity level. So it's been designed to meet the requirements for working on the ISS. We are currently working with Airbus Defence and Space on a metal 3D printer, which should fly in principle next year on the ISS to demonstrate. That would be the first demonstration of metal printing on orbit. And when it comes to additive manufacturing on the moon or on Mars, so as I said, exploration beyond low Earth orbit. So you see the ISS in the center of this picture and the moon behind it. So, and what we would do on the moon: resource exploitation, surface exploration, scientific investigation, as we are shielded from perturbations on Earth, for example, for radio astronomy, and the moon would be a training ground for mass exploration. So that implies a sustainable long-term settlement on the moon and later on Mars. So that requires infrastructure for sustainable exploration. And to make it sustainable, we need to maximize the use of the materials and resources we have at destination and reuse and reduce the dependence on cargo mission from Earth, which make the missions expensive and more complex. So we have been looking at in-situ resource utilization and in particular additive manufacturing, because it's a flexible set of techniques which can be operated in an autonomous way and which make efficient use of the material that you feed in. Some examples of studies we've been running. This one, the D-shape process using magnesium chloride as a binder. We built a 1.5 ton demonstrator, which you can see at ESTEC. And Foster and partner designed a concept for a habitat based on this 3D printing technique. So this involved the binder. We also looked at construction techniques without a binder, so solar sintering, using only concentrated sunlight to 3D print structures. It was a work with DLR, and we have also looked at the effect of neutron radiation on the shielding ability of this solar sintered regolith. We've worked with Austrian research company Fotech to look at the mapping of all the different ways we could combine resources on the moon to produce construction material or hardware material. And we made a demonstration using phosphoric acid as a binder to 3D print some small elements. We had a study about 2 years ago on looking at all the different ways additive manufacturing can support the building, construction and maintenance of a lunar base, looking at all the items which are needed on the lunar base and how we can use 3D printing to address those items. So we looked at regolith with lithos. We obtained very fine structures. Polymers, food, we've looked at living tissues as well, printed electronics. So there are a lot of ways additive manufacturing can help to maintain and build a lunar base. Our advanced concept team is looking at how to make fibers out of regolith and use it to make composite material for construction. They've looked at using urea as a geopolymer to make geopolymer, to use urea as a super plasticizers, and there again this could be reinforced with basalt fiber. And we have in our European Astronaut Center in Cologne, in Germany, a team called Spaceship ESC, which gathers interns and PhD students to look at various concepts for long-term exploration. So they looked at laser sintering of regolith, using regolith for energy storage and microwave sintering, among others. So this additive manufacturing effort, not only for exploration, but in general, is part of our advanced manufacturing initiative, which looks at all the promising manufacturing technologies which could offer a step increase in terms of design freedom, performance, cost, and time. So that includes manufacturing, but also other advanced manufacturing techniques such as solid-state joining or polymer processing, as well as computational modeling. So that gives you a quick overview of what we are doing in advanced manufacturing, in particular for exploration. Thank you. So that's it for my side.
Thank you very much. Okay, one moment. I think we've lost Henriette. Ah, yeah. Henriette? Yes. Thank you very much for your presentation. So, Henriette, you did not work with the group from Foster's, did you? Well, let me check. Advenit Makaya?
Yes.
Do I spell it right?
Yes.
Super. Henriette Pierre said that you have to leave soon.
No.
Good. Good, good.
I'm
I just thought, then it was a misunderstanding. Thank you very much for the very good overview of the advanced concept teams. You mentioned Marlies Arnhoff. You know that Marlies Arnhoff is from the TU. She was one of my diploma students.
Yes, I know. Marlies very well, yes.
She's really good, yeah. Shall we let the students ask questions, Henriette?
Yeah, it's a good idea, sure.
Okay, now, please, any questions you have is a good moment now.
We have some questions. Shall we just spontaneously ask?
Sorry.
Or shall I raise my finger?
No. I think when you ask a question, like Rudi, say who you are.
Ah, sorry.
Just to the other students and then ask the question. Thanks.
Okay. Well, my name is Rudi. Well, I'm a student at TU Vienna, obviously. And I wrote down some questions. So first of all, thank you for the presentations. I was really amazed by the. I saw it kind of. I didn't really see before the regolith fibers. I read about it that there are thoughts. There are some experiments on that, but not really done yet. And Advenit, could you elaborate a bit on what the current state of the fiber production of regolith is? It's very cool.
Yes. Yeah. So that's a project that my colleague Hannah Lack from the Advanced Concept team started. So the picture I've shown was the very beginning where they drew fiber from molten regolith. I believe it was in Heriot-Watt University in Scotland. But now Hannah has started the Ariadna project with Aachen University, who has actually a strong expertise in fiber drawing, in particular basaltic fiber. And the latest I've heard was that they can produce regolith fiber or regolith simulant fiber at relatively large scales in a repeatable way. So it's progressing pretty fast. And Henriette mentioned the call for ideas we had on first manufacturing and construction. We've had some ideas on fiber composites, so we'll see if they are selected. But this is a field which is progressing very fast and very promising.
Wow, cool. So you imagine something like building similar to, like weaving it together and building similar to carbon fiber in the future? Does it come close to properties like that?
No, it's not as strong as carbon fibers, but you don't need the type of mechanical properties on the moon as you have on Earth, because the gravity is reduced. So it's definitely good enough for structural applications. The difficulty is more into how you actually make the material on site.
Yeah. Thank you. Very.
I also had a question. Sorry, my video and audio are separated, so you might see me in a different image. Because you have mentioned, sorry, I forgot to introduce myself. My name is Emma, and I'm a student in architecture at TU Delft. And I have been working with Professor Henriette here within the robotic lab. So you have mentioned 3D printing with living matter. So I assume that you maybe have been looking into the use of biopolymers. I'm interested in what kind of material you have been thinking or experimenting with.
Yeah, so there are two directions we have looked into. The 3D printing of biopolymer was explored and is currently being explored. For example, to make biopolymer from food waste. That's something we are starting to look at with our partners from the Melissa project, but that's really at the very beginning. The other branch we are exploring is 3D bioprinting of organs. We've completed recently a GSP study on that, and it was quite successful. Our partner at Dresden, University of Dresden, managed to print bone, a piece of bone, as well as skin tissue. And the novelty in what they are doing was that the plasma can actually be used as how to say, a carrier material for the cells, which makes it very promising, because the idea with bioprinting is that you print, for example, skin tissue on demand for in case of wounds during a long-term exploration mission, and you could actually use the plasma of the astronauts to do that. So these are the two directions we're exploring at the moment.
Okay, thank you.
Yeah, ask one more question to Advenit and maybe Henriette. This swarm robotics, I thought it's very interesting from the project that was associated with Foster's. How far have you been in developing this swarm robotics concept for buildings?
So the swarm robots was actually not well. It originated from the work we did with Foster on the moon, but they matured this concept afterwards for application on Mars, where they have a swarm of microwave printing robots. And they briefly collaborated with the European Astronaut Center on this, but it was more of a concept at the moment. There has not really been practical demonstration of the concept. Now, in the call of ideas that we issued, the person who was actually doing that at Foster moved to Hassel Studio in another architecture firm in the UK, and he has proposed to work on this swarm robotic concept. So we'll see if this idea gets selected, but there could be some future work on that. But Foster and Partners, as far as I know, is working on other things, but not on swarm robotics.
I also have a question concerning robotics. I'm interested how important is the human factor.
Sorry, I cannot hear you. Maybe the sound is very low on your microphone.
Is it better now?
Slightly.
I will try to speak louder. I'm interested how important is the human factor by 3D printing and sintering, especially on the long distances, like, for example, commanding a 3D printer on Mars from the Earth. How important are the humans and how independent are the robots?
Yeah, that's a good question. So for ISS and to some extent for the moon, you can think about having teleoperation from Earth. And for the ISS, actually, the commercial 3D printer, which is on the ISS, is pretty much commanded from Earth, the American one. For Mars, you cannot do that because you have, well, you can do that, but you have 8-minute delay. So if in case of troubleshooting, you will always be delayed. So you really need to think about additive manufacturing capability with autonomous control or control from Mars itself. You cannot have operation from Earth. And yeah, you want as much as possible to have automated system. At least that's what we think. For one thing, because the crew's time is very precious. So you don't want the crew to spend all their time assisting construction. They will have scientific work to do and so on. So autonomous is better. Of course, you will need troubleshooting, and that humans can do.
Thank you.
I have one more. Sorry.
Go ahead.
I have one question for Henriette. I hope I pronounced the name right. And that is, you mentioned the Martian concrete, and that you would solidify it using a binder. And I want to ask: is this if the idea is to bring this binder from Earth or to produce it on site, or if you could go a bit into detail in regarding the Martian concrete?
Well, the point is, we did not research yet enough. Also, let's say, with respect to what materials are available. So our proposal to use Martian concrete relies on research that has been implemented in the US. But the ambition would be to identify what materials are available on Mars and then make proposals for how we could use those. So for instance, one of the speculations that also the students are going to present is that we could use, so apparently we could find silicon, or we could produce silicon similar material, and we could eventually 3D print with that. So, but I would be very much interested in what Advenit is going to say to that. So we are, let's say, we have been speculating about some possibilities, but it's all, so we have a bachelor student involved from material science, but could, until now, could not, let's say, have an overview with all possible materials, and then from there, what we could do with them. So hence is, at this moment in time, is still quite speculative in nature.
Okay.
Yes, I had actually exactly the same question for you. But yeah, I think the key here is to try to minimize as much as possible any component of the material that you would bring from Earth.
Yes.
And yeah, I can maybe provide some references to a couple of good reviews to your students to look into the state of the art.
Nice. Thank you very much.
I have a question for Sandra. Hello.
Hello.
Sandra, nice to meet you. I'm a big fan of your book. I use your book for my thesis. I just want to know if you have a study like more into gravitational factors on human towards astronauts on Mars, like how long they able to walk on the surface of Mars with a spacesuit, or how they live on Mars. Let's say even if we have a pressurized room, let's say. There will be interesting questions for future human space exploration on Mars.
If you want, there has been a paper, I think it's from Annette and Barrett, I'll find it, on movement on the lunar surface. The problem with these papers or with these researches is that nobody was there, and we don't know how to move in on a long term under these gravity conditions. And even on the moon, the astronauts had this heavy spacesuit, which was affecting the locomotion. So they did not move freely. But there's a paper that is an estimation, like counting, and maybe you can refer to what you do for Mars based on that. Also, I have another one, that another person I would recommend you. It's Ted Hall. Ted Hall is, to me, one of the specialists concerning gravity, artificial gravity. And
Okay.
I can send you a paper. He's a very nice guy. You can then write him an email for sure.
Okay.
He works at the MIT, and he is one member of our Space Architecture Technical Committee. So there is this Space Architecture group, and he's a long-standing member working on gravitation. I think the problem, or what would be interesting to research when hearing your ideas, what to do after the journey, right? You have a journey, 6 months or longer or less, a little bit, in zero G. Maybe not, it depends. Maybe you need artificial gravity on the journey. And then when you land, you have to work or function immediately.
Mm-hmm.
That is, I think, an open issue. And for example, Ted Hall and many others think that we will need artificial gravity somehow. It will not work that without, because I think so far you cannot reverse the effect. You can just flatten it or maintain it. But recently there was a video published from Scott Kelly when he came back, and it shows that it's not so easy to walk, and do things. And in case of emergencies, you will need some proposal for that. That's not solved.
Yeah, I read about it. It affects you a lot.
Can you send me an email? Send me an email,
Okay.
and I will send you the paper afterwards.
Yes,
okay?
thank you.
Sandra, should we move on?
Yes. Yes, let's move on.
Do you want to start?
As you like.
I don't mind.
Okay. I have 2 students. That was a bit difficult because they were all very nervous presenting today. So we have the 2 bravest groups. Rudi, do you want to start? Henriette, I think we said we keep it short, please, so we have more time for questions, right?
Yes.
One second. Wo er share screen?
Yeah.
Give us
a moment.
Okay. Du musst auch weitergehen. Screen einfach.
Can you see the screen?
Yes, we see me here. Can you see it?
Yes.
So, welcome to Mars. So this is like a brief of the fact that it would be the greatest achievement of humankind to settle on another planet, and that it's a harsh environment, so you don't have a breathable atmosphere, and it's also very dangerous radiation. This is Mars, and this would be our landing site, which is G0 crater. So G0 crater is located at an elevation below 2 kilometers below the mean surface elevation, which would protect a little bit against radiation. And it is also in a low risk area for the dose equivalent. It's also important to choose a location that is, from what I know, between -50 and 50 degrees latitude for landing physics. And it's also reaching very interesting resources. Like for instance, if you see here, it's a little spot for reaching iron, which is not very common. It's also rich in hydrated minerals, which is an indicator of maybe a possibility of finding ancient life. It's also not so abundant in dust, and has a lot of ferric oxides. It's also, it has 34 regions of interest, which is relevant for further exploration. Here you can see a little bit more in detail. So it has this geologic formation of a fan delta, which is also why there's a high amount of clay materials, and our choice for the base would be near this fan delta, so you can explore this, and also you could get further to the west through this river. And also it's near the crater walls, which are rich in carbonates and calcium carbonates, which is a good, I think, resource for further construction maybe. Yeah, and it's also in this planar area, which would allow exploration to the east. This is the vision for the project. It is not updated with our latest city design. Yeah, but it's somehow similar in the fact that we envision something like a positive future for Mars, where you could actually have these glazed domes that bring in sunlight, and you could have this like connection to the outside and to the nature.
And just by the way, the two people in front, they have spacesuits, but they are very lightweight already. So it's...
they are very stylish spacesuits. Yeah. So we will now present a timeline for how this comes into being. We were asked to make a vision and also develop like a first base. So we are kind of working from the vision towards the first base, and from the first base towards the vision. So it's like a two-way design. So this would be like a master plan for the city.
So yeah, and it's important to mention that we tried not to work from one direction only, so from the small parts to the big vision, because we found that when you only work from one side, you end up in the end not having a structure which works well when it's getting bigger. So we thought it's very important to always see both directions. So how does it look in a more final stage, so to speak, and how does it look at the beginning, and to really combine them. And this is also a thing we tried to,
and
solve.
It's actually really challenging.
Yeah.
So we kind of experimented with this hex grid. So this hex grid is like a good tessellation for any kind of area. You probably know it from like board games, and also suits modularity and expandability. It's also flexible. It can also like adapt to the terrain. Yeah, so these were like important points for us. We also have this division between where the spaceport is, where the city is, and where the industry would be. Also, maybe like power source would be not very near to the city, because it's would be mostly nuclear at the beginning. So this is stage 0, where you would have like only a robotic mission, or more robotic missions that would prepare the site for the first crew to arrive. They would build like a small habitat with a greenhouse. Here it's like a minimal subair reactor, because the focus would be to produce enough propellant to take the ship back to Earth. Yeah, and here we have like kilopower reactors that would be the main source of the first base, and also solar panels.
You need a very high resolution screen to see the things actually. So,
but they are here. And the stage 1 is when the next spaceships arrive with the first crew. Yeah. So this is the focus is to survive, to see if a base on Mars is feasible, to build further, to expand the habitat, and to research and scout and report. Also, nutrition production would be very important, so they could sustain themselves. This would be the stage 2 when it is accepted that the base is feasible and more people arrive. So you can see a little expansion of the habitat. You would have this modular expandability.
And this is a part, it doesn't really seem very, and just by the way, the mod, we will go a bit into detail regarding modules. But this part doesn't seem very, it's a big change, but actually we will see later why this part is very important, this bigger module now.
Yeah, so you had this little configuration at some point in with like 2 more crews arriving, you need for sure more space. So maybe the part where you did the research moves here and so on. Stage 3 would be when the thing expands even more, and also some industry is working. So you have a industrial part where you would produce more complex materials, like let's say something like a transparent thing to make a transparent greenhouse. Yeah, so this takes us to stage 4, where you would have the city like a pretty expanded base, which would look like this. You can see the reminiscence of the hex grid. So the idea is that you could expand in more than 2 ways, and you could attach to this connecting unit a number of different types of units. This is how it would look with the master plan. And this is we were asked to formulate 3 issues that are important for us, but we call them principles. So for us, human comfort, connectivity, and sustainability in a way are very important. So human comfort, of course, because you need to fulfill basic human needs, you have to protect against radiation and have enough food production to sustain the people there. Connectivity is important because you want to minimize the walking distances and also have probably like a synergetic use of functions and multifunctionality, and also because you need modularity for expandability. And sustainability would be like to generate some kind of sustainable energy and not rely on nuclear waste the entire time. Also, in situ resource utilization is obviously very important because you cannot rely on shipments from Earth, since this is very expensive. Yeah.
Yeah, now we can go a bit more into detail. Let's go first. Yeah, we also, of course, we haven't done something we would like to do is to have a real knowledge of how much mass we actually have to bring at the beginning. We haven't done the calculations yet, but it would be still obviously very important to at least have a rule of thumb of how much mass we are bringing.
Yes, so it is important what is available.
I mean, this is the biggest constraint for the design, obviously.
Yeah, this is like a diagram for what we think is needed at the beginning, and you can see how this can relate, so how the functions can relate to each other. This is also interesting because it can expand. You would have all of this in one unit at first, and then it could expand, so each function gets its own unit, or it can be a combination of 2 or 3. And every function needs some kind, in our vision, maybe not the same level of radiation protection. So you would have a sleeping unit that's more protected than, let's say, where you have your greenhouse or where you have like your training, because you don't spend that much time there, so you won't need that much resource or mass to protect it.
Yeah, this is this is still very, very diagrammatic, but this is a thought of how those modules could be constructed. I mean, this is not, we are not the first ones who have this idea. But first we would have this kind of inflatable structure, but then we also, because we have a mechanical engineer as our roommates, we talked a bit about the 3D printing, and we did some very, very rough calculations and found it's very time and energy consuming. But of course, it would be really amazing if you have the 3D printed structure. So what we thought of is, of course, this is the final goal where we want to get. But as an intermediate step, we would have because it takes a lot of time to print the structure, you would work with kind of a network of bags, which would just be filled with regolith. So this would be a very simple process. So you just have to take the regolith and put it in a bag, and put this bag in a smart way over the inflated shell. And because of the internal pressure of the inflated shell, we have a lot of force that could support the regolith bags. They're looking kind of thin here right now. This is a time thing, but
it's just conceptual to visualize.
So this would be immediate structure, and as time goes on, slowly they would be replaced by actually solid long-term 3D printed shells.
Yeah. So regarding expandability, you would have this first configuration maybe where you have the initial functions here with a separate greenhouse, maybe also separate sleeping units for like I don't know, safety reasons. Maybe this is more protected, and then we showed in the second stage where this connecting units come. This is also like important for the infrastructure, because this could lead to expansion to other clusters. Also, this is where you could add like a bigger greenhouse, because when you have more people inhabiting Mars, you would also need larger food production. And also here you can see like it would be like maybe like a research unit that has direct connection to the outside.
Yeah, and so what's just to to summarize it, what is very important here is that so this is really the initial unit, and the question really was, how can this initial unit expand and then still make sense in a bigger configuration? And what would happen is that, for example, before in the initial stage, the food production, the greenhouses would be in this unit, so it would be a closed system here. But then as it expands, this one would slowly move into the greenhouse, and for example, research facilities that were previously located somewhere in a compact way here would move here, and this would then be reutilized in a different way for more private spaces and sleeping quarters. Yeah. But then, so the important thing is to ensure that it makes sense at the beginning and in the bigger stage.
Yeah, and you can see it's kind of the same configuration, where here you have like a connecting unit to some other areas, and then it expands, like this connecting unit becomes this, and then you have different functions around it. Yeah, this was like a proposal for the functions for the city, where we also considered the synergies and how we could make them happen. Yeah.
Yes.
So thank you.
Thank you
for listening.
We hope our microphone was turned on, hopefully.
Yeah.
Thank you very much, Rudi and Miruna. I would let the guests start with questions, if you don't mind. Maybe the students from TU Delft would like to, or?
Yes, please.
I will start maybe. Very good presentation. Some very good points. The filling the bags with regolith is really, really good because at the moment we are talking about fancy processes, but implementation on the surface is quite far in terms of operating robots on the surface. So simple technique like sandbags is a very good first step for protection. You are talking about Mars, so you are talking about 6 months trip and a launch pretty much every 2 years from Earth to take advantage of the period where Earth and Mars are the closest. So everything that you take there to last long. I haven't seen a lot of food on your outline. How are you going to ensure that there is enough food in terms of shipment or local production?
So the initial thing would be would have also a greenhouse attached to it. So this would ensure for the food production. We didn't write it down, but we are thinking about maybe hydroponics. I think we've read that for one human being you need like a 50 square meter area of food production. So yeah, we are thinking about this stuff. We just didn't say it. Yeah.
Okay.
Sorry.
I was wondering about the use of materials, because you have this, yeah, and also about radiation shielding, because you have this like very large greenhouse which is covered in something that looks like glass. So I was wondering if you have any proposal of how that could be created on site, or bringing it. I think it would be quite heavy.
Yeah. This is also a question we ask ourselves multiple times.
Yeah.
And I mean, the first question we first have had to answer is how much protection is actually needed for each area and also for the plants. And we found a paper from NASA. It's actually a very pretty long document which went a bit into detail how much grams per square centimeter is needed to protect how much. And also there was this curve, this kind of logarithmic curve, which showed that the first 10 grams per square centimeter protect the most, and afterwards the
curve flattens.
The curve flattens, and you have less protection per mass actually. And so with this rough estimation of 10 grams per square centimeter, we said, okay, you would need maybe something around of 4 centimeter thick glass. But still, of course, this would amount in, and also it wouldn't only be glass itself, but of course we would have to maybe coat it with some special radiation reflective selective coating,
like a filter.
Yeah, but we're not always experts on that. But and that's also why this unit, the greenhouse unit, appears later, not in the first stage. So we're not saying, okay, the first day we build this giant structure, but that's also exactly why it appears in the later stage, and we expect to be able to produce a lot of the components on Mars, like with the Martian regolith. You can
extract minerals and produce different kinds of building materials. But so what is important is you have this cosmic radiation. Of course, you know about this, and you need mass to protect against it, and you need basically materials that are rich in hydrogens, from what I've read. So you could have like a water tank above it, or maybe it's a 2-layer glass, and in between you have some water. Of course, this is a really complex kind of construction, but maybe with like, I don't know, maybe another 20, 30 years of technological evolution, you would be able to do it. Or you would have like a polyethylene or some kind of plastic material that is also translucent, and you could layer it so you could generate this mask. So,
yeah. I mean, so basically, we are still investigating actually this, honestly. So we have some directions that could work. I mean, very simple. For example, you have so much internal pressure. I mean, compared to vacuum, that this like the main load factor for the structure will be the internal pressure. Like self weight is like 1/10 or 1/15 of all the forces. So layering it with a thin layer, like 5 to 8 centimeters of water, could actually be a structural solution. It could work. But yeah, these are just ideas. We have to dig in much deeper still. So we are not a bit confused ourselves as well.
Let me clarify one thing, because I had asked the students to develop the vision in 100 years first. And the reason was because I wanted from them to think big first. And then just a few weeks ago, I asked them, okay, how do you start? So I'm asking the students how to make it possible to realize the vision. That is a bit difficult, but I think Miruna and Rudi did quite well. I have a question concerning radiation to you all, because in the studio we have invited experts. We had, for example, 2 experts that said something a bit totally different on how much radiation shielding is needed. One is saying, okay, we don't have to forget the backscattering radiation. So you need 6 meters of shielding. That's why you have to put it underground. Another one says, oh, well, go for 0.5 meter of shielding. Or if you use regolith. Okay, if you use water, then it's something else. And I myself, maybe Advenit Makaya, you do know it. I myself was in a meeting, in a CDF meeting with SOM, where they discussed their lunar base concept. Have you seen that? Because to me, it looked like there was very little radiation protection. Or is this topic just put away because we don't know it yet?
Yes, Sandra, I was the study manager for the study with SOM, so I was there. Yeah, to make it short, at the moment, yes, we focused on the design of the habitat itself, which is an inflatable. So the radiation shielding in particular with the ISRU was not fully in the scope of the study. That's why we haven't talked about it extensively, but we fully recognize it's an issue for this concept. The idea was to have a regolith 3D printing wall against the habitat. We have also explored having water circulation inside the walls, but that turned to be a bit too complicated. So yeah, it's a thick regolith wall around, 3D printed around the habitat. That's the vision. Now, your question about radiation is a question I'm asking myself, because I have the same issue as different experts. You get different answers. There is no consensus on the required thickness, neither on the moon nor on Mars. They are still figuring out how to calculate this, and at the moment they have, as far as I understand, the simulation capability in terms of particle accelerator and so on are quite well understood, but there has not been any experiment on the moon itself. What I can say is, some experts will tell you, and actually most experts would agree, that whatever thickness you have, it will not protect you from the very intense solar events. So the only solution you have there is either to build underground or to have an escape plan whenever if you can foresee those events. So you have a shelter underground where everybody can go when there is an event. The problem is that it's very difficult to anticipate those events, and you probably don't have time to run for cover when they happen. So you can calculate a thickness, but at the moment we don't know how to protect against those intense solar events.
Thank you. Shall we allow one more question, maybe from someone else, before we move to the next one? Okay.
Sorry to monopolize the floor. I have a remark for this concept. I understand, and it's very good that you look far into the future, but to give a little bit of substance to your concept, you can start to think about logistics, because everything that you show in your concept needs to be brought there, either the elements themselves or the machines to build the elements. And that's a lot of things, a lot of weight to carry. So you had a little area for the landing of the launchers. You will need a lot of launches, even for your phase 0. Mm-hmm. So you need to think about that. As you said, you started to look into mass calculation. You will need to do that. How it translates into number of launches, how big your landing area needs to be. It will generate dust. How far can it be from the habitat itself? Think about mobility to transport the things from your landing site to the habitat and so on.
Yeah.
Amazing, man.
Great.
Exactly what we need to work on now.
Yeah. Thank you.
So, thank you. Can we have the next call? Doris, Alexandra, Bojana?
Yes, we're here.
Super.
Yes,
I will...
Hello.
Is my microphone working okay now?
Yes, I can hear you.
Okay, so I will start by sharing my screen. So first, I would like to introduce my team members and my friends, Alexandra Brajic, Doris Binder. So our project, Protocity. So the city is located in the mid-latitudes on the Mars, more precisely at the Bonstel crater. We decided to use this area after careful consideration on different maps from Mars, each representing a certain characteristic. We decided to use places that have a high thermal inertia, low dust index, available water ice under the surface, high amount of silicate, low elevation, which indicates a little bit higher atmospheric pressure, and the location that are the best for growing plants. So in our master plan, you can see how we decided to organize our settlement, or the city in this case. We decided to build the city around the rim of the crater, and in the middle of it to place our nuclear power plant. This shows that the distance between the city and the nuclear power plant will stay constant, which is minimum 16 kilometers, what is recommended on the Earth. Then also the distance from the city to the launch or the landing site we decided to use the distance of around 5 kilometers because of the possibility of the dust traveling long distances. Also, this site is good for us because there's also a possibility of the expansion to the other craters in the vicinity. Doris?
Yes, through this section of through our site, you can see we've been doing a study because of the wind and the sun path, and it's the idea of the expansion along the crater edge, and you can see a few distance kilometers to get a feeling of how big this is and the idea of the vertical living. This is the timeline where we, from right to left, where first there are going to be robotic missions. There's going to build the first unit. You're going to see it later. And then through time and through new technology methods and robotics and everything, there's going to be, it's going to be possible to allow safe resurfacing, bigger structures, variety of sizes, the thickness of the construction and layering. And yeah, this is the idea of the first unit, of the first home. This fixed part fits into a rocket that's transported to the Mars, and it got 2 inflatables with the same size and 2 floors. They're going to be deployed. There's also one smaller inflatable too, and the rigidest inflatable airlock. And the important part for us was to create the center with light viewing galleries in the middle part of the vertical garden and fruit production. And this is like a conceptual section through the first home, the first unit, where you can see this vertical garden and the galleries are gonna be around it. And also through the regolith part cover.
Okay, so the steps in achieving this would be the first step is landing an unmanned rocket, setting this fixed part that we have in the middle, setting up the inflatables around it, then covering it with the regolith, using swarm robotics to 3D print with sintering. That was our idea there. Then finishing the first shell, which is then safe for humans to arrive, and then adding a second unit after that, and third or more units, where we come to the part where we start to incorporate the smart shell. There we create atmosphere and remove the inflatables. They're not needed anymore. We recycle them for other use, and we then build with new materials, and we have more possibilities, various sizes of the shell, and more space in between that can be used better as only using the inflatables under.
So everything between these waves is gonna be connected. It's not each a separate like in the beginning. So that's the goal, to create a huge open space with atmosphere and covered with this smart shell.
So a little bit about the materials and the layers. We conducted a little study. So first we have these translucent compositions, which would basically be made either out of water or ice. However, the main requirements for such systems would be the thickness. So like monumental walls. Then there's a possibility of opaque walls and covers using a regolith. Also in this system, the thickness is also the main issue. And of course, there are some systems that, another opaque system using algae pockets as that have multi-purpose as oxygen production, radiation protection, natural shade, or bioreactors. And also another system, transparent system, using HB&NT silica glass. One of the reasons why we chose our location is because of this availability of high availability of silica and possibility of production of the glass, and HB&NT as a new type of the material that has high radiation protection and incorporated hydrogen that also heightens the radiation protection. Now a little bit about our city. So we see our city as like the first city on the Mars will become a blueprint for any other future cities on the Mars. So it's important to do it properly. And we know we face certain issues with this, like radiation, low atmospheric pressure, and also construction methods are very important. How to build on Mars. So to deal with radiation, we were thinking of incorporating smart shell and materials available from Mars, and some of them brought from Earth, necessary ones, especially for the radiation protection. Then to ensure a healthy atmosphere, we were thinking, of course, using systems like MOXIE, but our idea is to bring life from Earth to ensure biodiversity, not only for a healthy atmosphere, but also to ensure the long life of the society on the Mars. And then lastly, for construction, which will be at the beginning very limited, but we hope as the technology progresses, so will the construction methods, and we understand that the robotics would be very important in this step as well. So I think from my side, that's that. I don't know if my friends have anything else to add.
No, I think that's it. It's just the goal that the Protocity is here to directly on Mars. You can study the technology, how to build it, because it's not going to work if people from Earth are going to do the research on Mars or think about how we can build on Mars. It has to be directly on Mars. So that's one of the main goals of our Protocity. You're like testing for the future cities.
Yes, and I also would like to add that in doing that, we want people to feel free and to have the atmosphere and the possibility of walking around without their spacesuits, so they can also be creative.
Thank you.
That's it.
Thank you.
All right, thank you. Advenit, do you have something you would like to comment on immediately?
Yes, that's a very elaborated concept. That's very good. My first general comment would be on the material, for example, the radiation shielding material that you're talking about. You have to think about in what form you ship it on site. Do you ship the whole glass cover, for example? Do you shape it on site? Do you make it on site? Because that will affect your logistics as well. So that's my first general comment. But I think you have a lot of the needs there in your presentation already.
Yes, I would just like to add, we were thinking a little bit about BNNT and its possibilities. And because when we researched it, we found that the BNNT is, because it can sustain high temperatures over 9,000 degrees, they suggest that they would be good in 3D printing and sintering. Not sintering, I just read it's good in 3D printing because it can sustain high temperatures. So they would be shaped in like long in strands, and then used mixed with on site. Right now, we don't know exactly how. We're still researching how, but the research by now, what we know, research suggests that they can be 3D printed.
Yeah, and we also thought in our city to think about the big part where we gonna prefabricate and produce everything. So we still think about because of the infrastructure we're gonna need for that and how we're gonna do this. But definitely, it's a very important part, how to transport it on site and do it on site.
Can I add something? Because I thought so far that you are working on materials, possible materials that you can produce in situ.
Yes.
Okay, so there's no transportation from Earth, right?
No. I meant the transportation on Mars on situ.
But you are researching what materials you may have available, and then you think which ones you can use at which state, right? Okay, thanks.
So what's currently available: ice, frozen water ice, regolith, silica, iron on the surface, but we will have to bring something from Earth, like PNNT fibers, which we're still thinking about if they could be incorporated in the spacecraft flying to the Mars as radiation protection, and then reused on the surface of the Mars for the 3D printing on structures.
I can ask a question.
Of course.
So my question would be, I do think that this concept of having, let's say, a space where you have greenery and basically you have also the possibility to also enjoy being there. So it's not anymore, not confined to a small space. I think that's an interesting one. Have you been actually thinking about, because at this moment you have this mega structure, and then within this mega structure you're going to have other units, from, let's say, spaces where you do research to spaces where you meet people, etc., etc. So how is your idea about that? How do you want to implement it?
We don't exactly want to call it biodome, but it would be like a function of a biodome. So it could be a shell that's pressurized, and underneath it we would have like a regular houses, warehouses, schools, and so on. On the construction methods, we haven't really concerned ourselves with this phase. This is our dream, this is our vision. So we haven't really thought into details how we're gonna build this. But as you said, we are hoping that the technology will also advance on Mars, maybe even faster on Mars, because they will be under pressure to advance more fast than on Earth, I think. but certainly materials like steel, different types of panels. Definitely, I think that by this time, like in a few hundred years, regolith and water won't be used for as a materials for building anymore. So I think, I don't know if that answers your question.
We were thinking about the spatial arrangement underneath the shell, because it's gonna need at least at the first steps, it's gonna need more construction that holds all of this. And we thought about spatial tosses that will somehow make divide the space. And the point is that we want to have it flexible, so that because different functions need different spaces and heights and dimensions, so we wanted to create something like a spatial toss, so that you can fill these elements up with some kind of walls. We still have to think about the material, how and from what. It would be good if we could somehow create from in situ resources something, a material that has the effects of steel, but we still have to research that part.
Yeah.
Can I ask a question? My name is Arvin Hidding. I'm a tutor at Robotic Building at TU Delft. And I was wondering if you could go back to the slide where you showed a section of the site and your proposal. Yes, this one. So if I understand correctly, for the scale, your building would be almost 8 or 10 kilometers tall. Is that correct?
Yes, on some parts, yes.
So my question is, and also, so it's on the side of a vertical, almost vertical cliff. So in terms of production, you would have to figure out basically how your robotic devices are going to be able to navigate the terrain. But also in terms of the material properties, because if you are using local materials to produce the structure, just having the tensile and compressive forces of a structure with this scale, you would have to research the material properties. So do you have any vision on this?
We, like you said, we were here considering the vertical living. So at the beginning, it would be like horizontal, because you're limited with the materials. And few hundred years in the future, we believe it will be possible to make a vertical living. Now, I have some assumptions. I don't know if they're correct. So if I'm wrong, please correct me. If we are talking about atmospheric pressure on the Mars, it's 1% of the Earth's pressure, and we are making a pressurized environment under this shell, which would have Earth's pressure. So we are thinking maybe instead of, I think also we are how our building will behave when outside pressure is 100 times smaller than the inside pressure. Maybe then the forces will work differently. That's just my assumption. Of course, I'm not an engineer. I would like, of course, I would like to talk about it. But maybe, just maybe, then the conditions of building on Mars will be completely different than building on Earth. And then we are talking about different forces, I think. Maybe maybe instead of worrying something falling down, maybe we should worry about our smart shell trying to lift because of the inside pressure. Maybe it will try to separate from the other constructions. So maybe we should be more worried about how to keep it in place so it doesn't not fly out, but doesn't stay in its place. But yeah, I'm not an engineer, so I'm sorry. That's the only, I guess, answer I could. The way we were thinking, and that's the answer.
Yeah, we have some basic ideas on how it could maybe be possible to do that, but we are relying on our project, the Proto City, to experiment with materials and see on site how anything can be done, actually, because we can't know it if we don't try it. So that was the idea.
Thank you.
I think, thank you that you presented. I know you have half finished with the presentation, as you said, so, but thank you that you did. What I would like to conclude is, now listening to the question, is that the presentation is yet a bit unlucky. I agree with Henriette that for the vision as an architect, you should try to how to illustrate the properties and characteristics of the place. You know, the shell, the materials, you think about it, what properties you would like to have, and you propose which materials you think would be appropriate. But more important for you as an architect is to work on the architecture. So that's why I'm asking you, try to work on this image, and in that you see how the interior would work. No, it's not just wood. You should see some architecture, and you should see some spatial configuration.
Okay.
And I know that you're in the middle of the work. At the end, it should be more visible that there is this vision that has a conceptual stage, and your project that you work on will be more detailed. At the moment, it's a bit mixed, but from last time, I think it's good progress. We talk about it.
Yes. Thank you.
Thank you.
And maybe, sorry, also what Arvin said was a good point, because you mixed the presentation of a diagram with a section. And probably that's not the best approach, because you have two different presentations that are on a different level.
Okay.
Maybe the project should not look like a building already, or just maybe you should try to think how to show it more conceptual in these diagrams first.
Mm-hmm.
Okay, if there is not another question, I would invite the students from TU Delft.
Yes. Group 1, can you start?
Yeah. I'd like to share my screen.
Can you introduce yourself shortly?
Yeah. Okay. Can you guys see my screen?
Yes.
Okay. Hello guys. My name is Siddharth, and we were researching on this project since quite a long time. So this was like a studio work which we did in a week period of time, and where we were trying to look at the possibilities, what we could have to propose for off Earth habitats. So yeah. So the project which we were working on, so each team was working on different aspects. So that what our aim was to develop crop. Crop is cultivation robust operating panel. So it is an integrated design of 4 elements: plants, the structure, the sensor actuators, and the panels which are like very removable and how can they be operable in off-Earth habitat. So to start with, we were looking at, if suppose, so we already had like for the competition, we were generating the geometry, what would happen beneath the earth. But this presentation is more about focusing on the fragment, which we try to develop it much more further. So if suppose this is like a cave, like there's like a network of caves below the ground. We were looking at how could we take one fragment of it and explore it in much depth. So, for example, if you see, this is how it would look from the top of the surface, where it would have openings, like how you could go inside. And when you look through the section, we are thinking that probably our aim was to design like a biology lab for 6 people. So we're looking at that the sites could be used as where we could have all the green panels, and the center could be used as for life pods where the humans and the researchers could sit. So our aim was to, again, as I mentioned, our aim was to have like a Martian farm for 6 botanists. We were exploring, okay, which plants could we use? What are the possibilities to grow food on Mars, and dive into various possibilities of construction autonomously. So these were few of our references when we started the project. But so our main aim was to look into how do we construct it. So so when you see the sequence of construction, it is more or less like there's a as Henrietta already mentioned, like we're looking into rovers which are developed by TU Delft. So what happens is the shuttle lands on Mars. There is a Zebra rover which is currently being developed by TU Delft. It scouts the entire area and it sees what material, like how is the subsurface. It analyzes. After that, there is a construction robot which starts excavating, which is like milling in the entire space, and simultaneously it is also additively adding the structure to the entire cave. This is more of a like a schematic exploration, what we were thinking of how could it be constructed. We didn't like dive much depth into it, but we are just focusing on what are the possibilities to keep it more speculative. So after the cave is built up, the life pods are installed, and after that, researchers arrive with additional infrastructure. Uh, they put all the infrastructure, they put the plants either manually or by drones, and then they continue their research in the life pods. So our aim was to like look at a fragment and see whether all these ideas work or not, to see at what level could the speculation go. So our idea was to develop a fragment, which is like an integrated panel which is able to host plants. So this fragment is like, if you see the cave, so we chose a fragment from this part and we tried to develop it. So you can see like it has various layers to it. So what happens is basically, firstly, what would happen is the back white part, that imagine that as being the cave walls. So to first, when the milling is happening, like the excavations is happening, after the excavation is done, there is like a shotcrete concrete layer which is sprayed over the cave so that it could have like temporary, it could hold the structure. After that, we had structurally optimized, so as Henriette had also mentioned about structural optimization. So we also did like a stress analysis on the entire cave to see where do we need the structure to be, so that it is materially it is efficient, and uh, it could hold the entire cave. And we also embedded sensors and actuators in the entire panel. And then there is like a covering which is like the lids which hosts all the plants. We also looked into which plants which we could use from research from other researchers. So to die like this is like an overall summary of what the fragment is about, but let's try to understand how did we achieve like reach over here. So we did like a stress analysis on the entire cave, picked up a part, studied. So ideally, what our aim was that this would, so based on the stress lines, it tells us where do we actually need the material to be, and we can remove the material which is not needed at other places. So the stress lines will spread on the support points, and through this process we went into form finding of using computer optimization based on material properties and stress analysis. We can describe the shape as an optimal one. So this is the one which we found the most optimal, where it can take all the stress in the cave, yet it is materially it is very efficient. Second, what we were looking was acoustical properties, since it's a cave. So we are also looking at, okay, if you see the entire geometry, it started initially with a Voronoi pattern of how we could deal into Voronoi cells and how they could expand. So we wanted to continue the same thing in the same idea in the entire cave. So what we are looking at options, should we have like an embossed layer which acts as an acoustical? Should we have like something which is extruded or something which is very subtractive? So based on this, we thought that having this, the third option works the most best because you're using less material and it is performing. So we also did like an analysis. If there's like someone speaking in the cave, so how would uh, the sound behave in that space? We also did prototyping with the sensors. So when you see, so till now what I explained is how the structure will stand. But now if you want to put plants, how does the sensors and actuators work? So we did a small prototyping to see how it works. So this is like an entire scheme which is there, like the entire sensors consists of like various different sensors. There is like a heating cluster, there's a humidity cluster, there is all, it is also connected to irrigation system, and it is completely controlled by Raspberry Pi. So this is one setup, but we wanted to test this in real terms. So what we tried was we did the entire, made the script and see whether it works or not. So what it does is the script actually sees how, what are the water, it measures the water level. It checks what is the humidity, what is the temperature, what is the UV, what is the IR required. And when you run the script, it actually at every second it will give you feedback. And similarly, we did this, and also if this entire sensor could also control the irrigation system. So if the water level is low, it informs the user, and later using sensors itself, we could give water to the plants, and the whole system could work. So this was more like a prototype which we tried out. These were like the various sensors which we might uh, sorry these are the various sensors which we might need in the process. So for the landscape part, we wanted to use like an aeroponic system, and we also were researching about it, and there was a professor from Wageningen University who had already researched like which plants could grow on Mars, and taking inferences from there, we figured out that these are the possible list of plants which are like which are you can grow on Mars. So the whole idea again was to we have like removable lids. So lids are 3D additively manufactured, and the plants could be installed in there, and the aeroponic systems doesn't require any soil or something. What could easily happen is like they are first grown in a nursery, like in the life pods they are grown, and then either by using drones or manually it could be put into the system where it can start to grow. And so if we see the section, it's like this is the lid, this is the plant, and you have the sensors and actuators behind it, which is giving it water and vapors so that they can grow. This is we were not able to completely yet try the prototyping. Like the whole studio was about that you develop the fragment and then you actually prototype it in 1:1 scale. We were not able to do it due to time constraints, but then it is all about, we still made how it would be constructed. So how can we mill the space? We made it like millable, and we tested it whether it is working or not. And we also for the structural scheme, how can it be 3D printed or not, using so yeah, this was the work which we done till now. So the whole idea was to look into possibilities of how can we develop this one fragment, and then later test this one fragment at 1:1 scale, and then more test whether this theory works or not, and look at more future speculations. Thank you.
Yeah, thank you, Siddharth. Are there any questions?
Yes, Harriet. The dilemma between for construction of habitat on the moon and on Mars is surface or underground. And one of the big factors to determine that is the difficulty to excavate. Have you looked into how hard it is to excavate on Mars?
For now, what we are trying to do is for excavation, we would have like that same robot, which is so first the Zebra rover comes on the surface, it scouts whether, and it tries to analyze which surface, which part of the site is like actually excavation is easier. And then we use the same like there's another rover which actually excavates and prints at the same time.
Yeah, I suggest you look into data on the soil itself, the density of the soil and so on.
Yes, basically we asked a professor from civil engineering to join the team. He did have a look at the soil composition, and his first impression is that the technology that has been developed for similar situations on Earth could be applied on Mars too. So basically, with this in mind, we proposed using the rovers, but of course the rovers would need to be equipped with the drilling heads that would implement the excavation.
Okay. Okay. Now, if you've already talked to someone with knowledge on the Martian soil, then it's good.
Well, basically, ideally, we would like to continue this research. So, in principle, we would like to even test some of the ideas.
Okay. Henriette is lost.
I think so.
Yeah.
What she tried to meant was like the team is now expanding slowly and slowly. We have people from material science. We have people from civil engineering professors who are
Human robot interaction as well.
yeah, human robot interaction as well, like in the entire TU Delft. And right now we are just looking at speculative models of what are the possibilities, and then based on these we try to test whether like using feedback from very various disciplines, we try to integrate whether how we can make this actually possible.
Yeah, so the design of the habitat itself would also be informed by which robots we are using, the reachability of the robots, the printability of the structure. So for example, that structure optimization angles would be sort of within the tolerances of the printing angles and within the reachability of the robotics. And that of course depends on the material properties. So and also in combination with acoustic optimization. So the goal is to make an integrated proposal for all of these different aspects, so that in the end what we are proposing is feasible and integrated in one parametric system. So we also take, for example, the input from the civil engineering. So the plan is, for example, to first scan the surface with the deep ground penetrating radar to figure out where the surface cracks and surface defaults are and what are the properties of the different layers. And then we would, based on this information, we would generate a 3D model in the ground where it would be feasible for excavation, and also feasible in terms of the architectural requirements and the functional requirements. And then based on the robots that we have, generate the different procedures to produce this system.
May I add something to the presentation?
Yes.
I just asked Siddharth to open his presentation again, because first of all, I like the presentation a lot. I think it's very interesting concept, but I have a suggestion, because the third slide and the fourth slide, it looks like it's very flat terrain. And as I see your project, or as I listen to your project, you have not chosen a specific site. You're going for a prototypical implementation, right? So
yes.
So I think you could propose like 3 sites. One that is very flat, one that is very sloped, and you could create a conceptual image when you go to 7, for example. And maybe you can have one that is not digged in, or where you don't need to excavate, but where you pile up. Because the issue of your project is not the bagger issue, right? How much infrastructure you need for the bagger, it's your whole prototype. So maybe if you have 3 different settings or possibilities, how to implement the big vision, and if you put it on top of the floor and you pile up, it has the same effect, right? In terms of radiation shielding.
In principle, basically,
Okay.
I think we have lost.
Yes, yes.
Yeah.
But she's coming back.
Okay.
Now you're here again. Andrea?
I'm back.
Oh, yes.
Yes, sorry, I was again off line, so that's already the second time. Sorry about that. Basically, what I wanted to say is that in principle, underground, I think this was confirmed also by Advenit, that underground is the most safe area. And the other point was also that the temperature differences are less. So hence, this is why we wanted to go below ground. Also, at the same time, as space, at the same time you are mining for materials that you can use for building the habitat. So, but I can see your point that in principle, of course, also been building interesting to explore.
I just thought it would just take some critics out, because then you could communicate more about this wall system. It's interesting.
I have another question. I hope I didn't interrupt anyone. So I really like it's a very cool idea with this kind of multifunctional wall you have here. One question I have is, did you think about the circulation? Like how does the entrance look like? I mean, how can you get in? Do you have like a elevator? Do you have steps? Do you have like staircase? And how you can maybe, like, for example, put something on the ground? Is there like some system you have thought of?
Maybe I can answer that question. So this is the result of a workshop that we did, where the focus was really on developing the fragment and the material system. So we have developed several prototypes and several fragments, where each group has focused on a slightly different material system. So after this, we plan to develop the whole habitat further, where we basically take the feedback from the production experiments that we have done, and then take those into consideration for the design of the entire fragment, of the entire habitat.
I would also have a question, because obviously this is another scale than what we are working on. So you showed that you have some optimization. So I guess these perforations that you have in the wall come from the acoustical optimization. What comes to my mind is that probably the wall would perform differently acoustical if you add the plants. So there would be another absorption rate or reflection rate of the sound. So maybe you should do like this acoustical thing should be after you add the plants, or you can incorporate this with the acoustical optimization.
Yeah, I would agree. So the whole point was, without the plants also it performs well, and if you will add the plants, because plants are good absorbers for sound, so that the whole space would also work in much better, like it would perform much more better when we add the plants. Definitely.
Yeah, that's cool. I mean, it's a very interesting interdisciplinary project, and I like it a lot. Also, what I wanted to ask is how much time
does it cost?
Yeah. How much time did it take for you to develop it up to this point?
We actually just this was like a 1-week workshop.
We started in February? No, March.
No, the entire proposal, the one which Henrietta proposed to you guys about the first one, where we were having the one image which she showed, that we started in March. But then this idea of developing this idea was more or less done in like 2 weeks.
Whoa.
Where it was like ideation, because it was more about depth. So when you see these ones, these are just about speculating possibilities.
Yeah.
But the main focus was on the fragment, how we can develop the fragment using structural optimization, acoustical optimization, to integrate sensors and actuators, and to also integrate landscape into it. So the main efforts were into that. And we were like a team of 5. So each were taking different roles. Like one was looking into landscape, one was looking into sensors, other one was looking in structural optimization, one was looking into, so it was more like a team effort where everybody was focusing on some of the elements of the design, and then we just integrate it all together.
Amazing.
Sandra, I think we need to move on because we still have two groups.
Yeah.
Yes, please. Let's move on.
Yes, unfortunately, I will have to leave at 12:30. So I apologize for the 2 groups we did not see.
Thank you for joining.
Thank you very much.
Until now.
Thanks a lot. Very good feedback.
Thank you.
Shall we do one group photo?
Yes.
Yes.
But Henrietta, do you know how this works?
No, no.
Anybody of you?
I'll take the pictures and I can share it with Henrietta.
Okay, super. Can you turn on your cameras all for 2 seconds?
My camera is not working.
Ah.
Oh.
Okay. Shall I take the picture?
Yes.
I think there's some
please.
people still trying to on the cameras. But yeah, I think we can go for the first round. Yeah.
So now we can stop freezing.
Yes.
And move to the second group. Thank you, Siddharth.
All right, should I share my presentation?
Yes.
Yeah. So let me see. Are you able to see my screen?
Yes.
All right, so this is also part of the workshop that we have been developing with Professor Beer. And it regards, again, construction, underground construction for the reasons of shielding from radiation. So our group has developed a project around the theme of layered porosity, layered not in a traditional sense, but in a 3-dimensional one, and porosity referring to the materiality of the project, so basically to the logic of construction. And in this presentation, I will talk about the computational logic on one side and the architectural functionality of the project. The basis of our concept was the Voronoi, so it's a mathematical way of redistributing geometries in such a way that they can be controlled by cloud of points. And then basically this is applied at a larger scale of the whole habitat. And in this way, we're able to control the spaces. So for instance, by controlling the cloud points, the cloud of points, we're able to create spaces of different size based on the needs of the astronauts. So for instance, a larger space that would be used as a dry lab, or smaller spaces that would be used as sleeping areas for the astronauts. The system is componential, which means that basically, as you see in this diagram, you're able to expand the system as you go based on the needs and based on the evolution of exploration of space. And from the large scale, I want to zoom in into the componential scale and have a look at a fragment that we have explored. Basically, on this fragment, we performed a structural analysis, and the reason was to be able to understand roughly the tensile and compressive forces that are at stake in this fragment that we studied. And these respective stress lines were then used to inform the point cloud. So basically, you see an array of points, and these ones are creating the Voronoi cells. The idea is that by basing the Voronoi cells or the structure on the structure analysis, then we could have the density of the points and also the structural stability of it corresponds with the amount. So it increases in proportion to the amount of loads. So in this sense, the Voronoi cells are structurally optimized, which means that we only depose material where it is necessary. But this, let's say, like this Voronoi structure is also informed by architectural functions. So for instance, because this fragment considers, well, it's basically a part of a room, which is destined for sleeping and socializing, but also some light work. Then the point cloud, it also is informed by the functionality. So for instance, the necessity of having a bed or some storage area. So the idea, this is a section view through the fragment. And here you can see a bit more locally the differences in gradient. For instance, the areas which, most of the horizontal areas in terms of comfort, so for instance, areas on which you need to walk on or on which you need to lay or sleep, have a bit of higher density so that you can recognize in the pattern. But then you have an area like the middle image over here, where you have some bigger Voronoi cells within the wall, and those can be used as a storage area. And from here we can go a little bit into some details of the habitat and see, well, basically these Voronoi cells are organized on a logic of positive versus negative. So the negatives are the ones that are sculpted in the wall. The positives are the ones that are sculpted out of the wall, which serve as, for instance, furniture that you can sit on and use further, or a sleeping area that can be reached via staircase, but can also be used as an area to relax and breathe. And finally, the part of robotic production, we have basically explored with the use of EPS. So we have used robotic milling in order to explore, an analog. So it's an analog of the excavation process that would take place on Mars. And basically in this way, we were able to explore the milling toolpaths that are an analog of the excavation process that would take place on Mars. And yeah, this is an application that we have been looking on. These are the final toolpaths that you can see. So with this, basically this part of the project is an exploration into the materiality of space. It's an exploration into the use of local materials as much as possible, but doing it in a very economic way, so only having material where it is necessary. So because that would help with the use of material, but it would also contribute to saving energy, because energy is very precious, as we know, and as well as creating a habitat that can be adapted to the needs of the astronauts. So as you can see here in the beginning, we have been looking a little bit of dividing the whole habitat into these cells and applying it from a large scale to basically the scale of the material, the wall itself, and possibly exploring it also with objects. Thank you very much. Are there any questions or comments? Were you able to hear my presentation?
Yeah, thank you, Emma, for presenting. It's a pity that
Henriette, I think we lost you again.
Yeah, very bad connection. Can I ask you a question, Emma?
Yes, sure.
Thank you for your presentation. Very, very interesting, beautiful work. I have a question concerning the parameters for these different activities. What have been your parameters? You probably said it at the beginning.
Yeah, so yeah, I think we have parameters at different scales. So basically, if we look at the large scale, then this segment hasn't been explored much because we focus on the fragment. But the idea is at the large scale, the parameters would be the needs for certain functions or certain spaces, like architectural spaces. And then, so then the logic of the Voronoi would be used to divide spaces. But then at the scale of the fragment itself, so for instance, if you look here, yeah, I don't have the slide over here, but basically we have two sleeping spaces, one here and one here, which are also shaped by a Voronoi. So basically, the Voronoi logic goes from the very large scale to the scale of the habitat down to the scale of basically the materiality of the wall. And in terms of parameters, yeah, the beds are basically shaped considering human scale,
So,
as well as the habitat.
So you took the body of the human as a cocoon that you will have to surround. And did you also consider activities within the sleeping? I mean, sitting upright, getting up, getting down, or sleeping with someone else in one bed?
Mm-hmm. Yes, so if you can, I can show you here. Yeah, for instance, yeah, if you look at the fragment where this is made, it's over here. And the bed is basically reached. So this bed is at a higher, it's kind of like a bunk bed in the wall, but it's reached via this staircase. And then on the side of it, in order to prevent, I imagine like you have a person staying here, in order to prevent that this gap of height would be problematic, we have some furniture corresponding in an office, yeah, let's call it a table and a sitting area. And this would be another place. But yeah, also in terms of the shaping of the bed, it does include, yeah, so we try to play with it, to work with it, so that it can also be used for just like laying on your back. So it's more user-friendly and it can be flexible in terms of use. But yeah, I think it's interesting to consider also yeah, what the comments that you added to people.
Because I mean, I think it would be interesting to add another person, even if it's not, you know, your partner, but maybe you want to stay with a friend as well, or I like this presentation a lot. It shows immediately how this beautiful structure works. I think it's good to have this people in the drawings showing what they do, because you don't need a description for that. Is it and one more question, please? It is not changeable right now, as I understand, but have you sort of like destroying parts of it, using the material and renewing it? Or how would you change form? How would you change form or function?
We have discussed with Professor Beer, and it's a concept that we still need to explore, componential logic. So basically, yeah, also in terms of the expansion in, so if you look at the large scale of it, you start with some components, and then you have to think about how basically the habitat evolves so that it continues to fit the structure that has already existed. And yeah, in terms of the structure of the materiality itself, we have considered being able to, let's say, work with it so that it can be repaired, or maybe having modules that are fit together instead of having a whole surface, so being able to take parts out and put others in if they need to be repaired. But we haven't developed that part. It is something on to think about.
Yeah, go on.
Easy and maybe not easy question. The first question is, you showed at the beginning these kind of stages, like how it develops. Did I understand it right? If you go in, yes. Yes. So is this could you explain how you are imagining it? So it basically grows, and as it grows, it goes deeper and deeper, and it's being milled, or it's being excavated, and the surfaces are milled and printed. Or could you explain how this structure will grow, or how you think it could grow?
So as Professor Beer has mentioned in the beginning, we are thinking of the habitat developing in terms of an excavation of a spiraling path. So basically, you would excavate in a spiraling path and build in the same time. So I would imagine the habitat developing in depth, but we also have to explore basically the mechanics of the soil in that perspective, but it could also expand sideways, so to say. I think why we chose the Vorno in the beginning, and we had quite a broad discussion about it, was that it contributes to economy of energy, also in terms of if you have two rooms that share the same wall, compared to if you have two different habitats which are separated, then you're saving materials and you're saving also time and energy of moving from one place to the other. But yeah, that's something that we are working on, and we have to explore a little bit more on the soil mechanics to see what are the possibilities. I don't know if somebody else from the team has comments on that.
Yeah, I think.
But I think, yeah, that's my answer.
So basically, sorry, maybe I missed a point. So basically, you're digging the structure, and it's digging deeper and deeper, and you're reinforcing it with this Vorno structure on this circumference.
Yeah. So basically, that as you dig, you also reinforce the walls of the corridor that you dig, because otherwise, let's say you have dug 4 meters, 5, and the structure could collapse on you. So the idea is there are some rovers, so there will be a swarm of rovers. Maybe some of them will be specialized, or they will have different functions, where some are digging and other ones are processing the material, and others are reinforcing, so building the wall. This would be the process.
And just very quick, the second very easy question. What for the milling path? What plugin did you use? Did you use like Kuka PRC, or what software did?
Yeah.
Yes. So you used the Kuka PRC?
Yes. Yeah.
Okay, very cool. Very cool. Nice.
Yeah, so now we are using the Kuka PRC because we have a Kuka at our robotic building lab, but in the end, this will be replaced by simulation that matches the the actual robotic device that will do the excavation itself, so that we have the accurate simulations.
Very nice. I really liked it. Our cooker at the university is a bit dusty, to be honest.
It's never used.
Okay, shall we, Henriette keeps this disappearing. Is there one question from someone else? Emma, would you like to have feedback on a specific content?
Well, I think something that I haven't mentioned and maybe is a part which needs to be mentioned is that we have considered also the inclusion of, or maybe this, yeah, so we're still thinking about how that would work, the 3D printing of inflatable material. So that could be done directly on the surface that you see. So it's something that we have been developing on. I think one of the things that which I'm interested to know your opinion on, and which we have also discussed. So we've had a discussion with Professor Angela Vermeulen, who has done studies of living in isolation and confinement, which are basically analog missions. And he was talking about the tactile feeling of the wall. So this is, I think, something that we have invested some time on, because the environment in which astronauts live also needs to be basically pleasant to live in. And that's also a reason why we have different gradients which are associated with functions. So I'm curious about what you think of the tactile feeling of the look of this fragment.
It's interesting that you mention. Keeps reminding me of my professor, former professor. He was this, because there is the scale of, you work with macro to micro. Can you go, I like it because it seems that all of you do this. At least in the previous presentation, I could see the same concept. You have an idea for the macro and then you go in between and then you work something in detail. And it's interesting, maybe you can see what is the difference in perception. Because what you say, the tactile feeling is important. Right now we are sitting on the table. It's important how the table touch feels. Yeah, when you look at the laptop, it's important. Maybe it's even assisting which one you choose when you like the touch, you know, of the material. But also, in addition to touch, vision is also different in macro and micro. There is this proxemics, theory of proxemics, maybe you know from Ted Hall, I think. You know, with this private space, social space, and more public space, that we all have this space where we don't want someone to enter, except we allow. And this private space is for sure very much important in these mini housing projects, micro houses, where you live together, not with your family, but with colleagues, with people you work with. So this separation or combination of what is mine, only mine, what can I share? This is why I'm asking you, maybe you want to implement a space that you can share if you want, like inviting one or two into your space, and then the space for all. So this could be interesting as a parameter, you know, one place that fits all is typically for having dinner, having some meetings to discuss something, doing sports. And then you have places that are only for one. And that concerns also storage, for example, or lighting in the space that is yours, your own. In this bigger one, you would like to be the chief of lighting, heating, coloring, you know, decoration. And maybe this is interesting that you can say there is one part that can be more individualized. Maybe with the help of a computer or without, maybe the sleeping HOTS look different or can look different, because now at the space station, all the astronauts have put some territorial objects, you know, around the place where they sleep. It's the group quarters, the private place is the sleeping quarters in the space station, and they all use objects and to indicate it's theirs. That can be interesting, how to individualize your space or how to characterize your space, same as choosing your clothes. When you want to show something when you choose a certain type of clothing, and probably there are times that you want to show, this is mine, please come in, stop, without having a cross light, right? Without saying red or green. It should be a place maybe that is cognitively readable. So for one example, in, as you said, simulation centers, is this door open and door close. They have found out that the people are using this, when it's closed, everybody knows it's closed, don't enter, don't knock, leave me alone. When it's open, it gives you the possibility to look outside into the bigger room, to be part of what is happening in the social space, but at the same time being a more protected, you know, not outside. Or it can also mean it can also mean, okay, I'm open for a conversation. If you want, come in. You know, things like this, so situations.
Thank you, Sandra. I have another appointment soon, so let's maybe move on to the last presentation.
Yes, hello. Can you hear me?
Very well.
Yes.
Hello, I'm Yiri. I will present for the last group.
Yuri, we don't hear you very well, though.
I'll change that. Is it better now?
Yeah, it's better.
I will try to talk loud then. Yeah, our project is, well, the scale of our project is it's quite a different scale than the other project we saw, and it's good that the two other projects were before us, because in this presentation we do not really focus on the shell itself, but we mainly focus on the panels we created and the structure of these panels. So we are group 3, and these were the people from the group. And yeah, the aim of the design is to create a highly functional system of 3 layers. A milled structural layer that's based on the stress line analysis of the regolith itself, and a vital additive reinforcement layer of metal and silicon, and an acoustic additive layer that's 3D printed out of the milled regolith. So this is the structure we have already seen, and that was given to us for this project. We structurally analyzed the shell and selected one of the more challenging junctions, where there's a concentration of multiple surface curvatures and resulting forces. And the actual prototype we were managed to make was only 500 by 500 millimeters, as you see here. So basically the design is based on 5 different layers. The Martian regolith structural layer that's built. We have a sintered reinforcement layer on top of that. Then we get a silicon. We have a connector with the connecting panels, and the panels are made of Martian concrete acoustic, 3D printed layer as well. So first, the structural analysis of the shell and the fragment. We analyzed the shape using the loading conditions, and the results indicate tension in the more projecting parts of the fragment and compressive forces at the more recessed parts of the fragment. And after that, we generated the stress lines to indicate the most optimum position where the reinforcements in the form of robotic sintering can be done on the surface of the regolith. So the process of laser sintering we talked about already in the beginning. It's a process of that's being researched. We found out in the Space Center Johnson in Texas, and this in situ process of lasering and heating up the surface, and by that try to bound the metals and melt them on surface with the right temperature. So we did that using the stress lines, and the stress lines therefore are simplified, scaled, and converted into a sintered layer. So as seen in the third fragment here. The Deaton spaces are milled and function as a connection with the additive layer, and the result is a structural optimized panel. So we go again to the research we did. As well, what Henriette discussed already in the beginning. NASA, the Curiosity rover in 2015 discovered a large concentration on silicon, and that's why we as well try to use silicon in the reinforcement layer as an airtight layer for the whole structure. And as well, we will reuse the milled regolith and use it as the printable for the printable additive fragment as well. So then, in between the two fragments, you have the structural reinforcement layer, and this is the design of the connector element between the additive acoustic layer and the subtractive regolith layer, with two female elements. And one male connection, and the connector will provide an air tightness between the two layers, as said before, with a sintering layer first, and then on top a silicon layer. Then we focused on the additive part, which has changed focus towards not structure anymore, but an acoustic purpose. So we did, we analyzed different kind of panels that are well known on Earth, and try to do analysis on them with Grasshopper, and trying to find out how the diversity works when you shoot on a sound simulation. And after that, we integrated other necessities to the panel, as cleanability and printability. And with that, we finalized. And here we have the development of the different options, and what their cleanability, printability, and acoustic qualities are. We finalized the design with a form based on the Gray-Scott model. That created a panel. It's a pattern of a simulation of two liquids, and the advantage of using a simulation model like this is you create a reaction that you can control, but at the same time will have a certain organic randomness, and that will contribute something from Earth's nature in aesthetics on Mars. And then after that as well, we simplified it, we scaled it and converted it into a printable layer. So that were the three different layers I went through. And now we will go into the robotic manufacturing approach, where first we will mill and subtract in the surface, and after that the stress line will be laser sintered for create a structure, so the regolith won't fall off or won't collapse. We have a dense laser sintering after that as well, and a caulking gun principle for the silicon layer at the last point. So the surface we pick, we will mill in that surface. After that, we'll have the sintered reinforcement layer. You will add the metal sleeves, and they will come as far as possible from the stress lines to avoid destroying the structure. After that, we have the silicon layer, the metal connectors, the mill connectors will come in, and then the acoustic panel can be placed robotically exactly on the place. And after that, you have space for sensors for electricity or other purposes of the surface of the shell. So we were able to start a prototype where we choose different bits, of course, the more rough bit for the first. I hope, yeah, the movie starts. So first, of course, you mill as rough as possible, and after that we have the second, more rounded bit that creates the proper shape in the first milled model. When putting the lines closer together, you get an even more smooth surface with the same bit we used after that. And then for defining the contours as well, something that is for the sintering important to do, we used a really small bit for the more precise work, which you see in the model in the middle. And we were as well able to print a prototype, which is now, of course, in plastics. So it's not original material, but still it was really nice to see how the two afterwards came together. And yeah, I would like to conclude with the fact that we were really aware of the fact that we had to do some assumptions according to research we did, but for the laser sintering and the silicon layer, we just used this technology in our proposal, but more research needs to be done on that point for sure. So that was it.
Thank you, Miri, for your presentation. Any questions, comments? I would like to comment, maybe. So it's, of course, it's a pity that Advenit is not here with us. So I think I'm going to have to contact him later. But I do think that it was quite successful that you managed actually in the time, allocated time to go through all phases. Still basically the additive layer, and this I discussed already with Arvin, is not quite a prototype, right? Because actually the material need to be deposited everywhere, not only as a contour line.
No. There will be as well a structure inside, but it won't be a full panel, but it will be structured inside for sure.
Yeah.
Yeah. And as well, like the lines are not as sharp as we thought. We were as well not able to see the model in real life, of course, so we do not have a real feeling of the first prototype, but it's a bit smooth, I think, still.
Yeah.
So lot to work on as well for the panels.
Yeah.
But when you say that, maybe it's interesting to work with two different materials, because it's also, in architecture you can also have some panels where the outer, the one that is exposed to the human uses, human activities, has different characteristics than the one that helps against acoustics. So the one that for acoustic could be softer, and the one that is shown to the people could be a bit more resistant. Maybe it's not the worst idea to have two materials. What do you think?
Yeah,
we did that on purpose, actually. Amongst others, also. Yeah, go ahead.
Sorry. Yeah, we tried to get the print. Yeah, the action of the printing itself as easy as possible. I think in that way, and we were like using different materials. We were already discussing actually about using the four different materials we have now, like the metal, the silicone, and the regolith. So we try to minimize the different materials in the project. But I think, yeah, to use a soft acoustic panel, a soft material for that would have been was a discussion as well. Would have been an option.
Because I was thinking, when you use, for example, you have a wall in the laboratory, and usually walls in the laboratory need to be more flat. And when you have something, as you said, you have the panel and you don't see what is behind, and behind with some holes, and behind you have this acoustic world, then you could have the same prototype, but according to the room or space it is applied, it can be more spacey, like these prototypes. I mean, they look really beautiful from the geometrical point of view, but there might be spaces where you don't want it, just because you want to clean them easily or whatever.
I have a question.
Yes.
I want to ask if the pattern, like, why do you make it straight instead of curved? Is there any explanation? The pattern is straight rather than curved, like structural wise, or beneficial?
On which pattern? The subtractive or additive?
The second image, the robot.
It's more an aesthetic approach. The subtractive one is completely built up from the structure point of view, and the additive one was acoustically printable and easy to clean. And afterwards, we got the Gray Scott approach, and we wanted to have like the acoustic panels like more pointy to diffuse the sound, and as well we wanted to have the deeper points and the higher points to be able like we have so we have spaces to have the electricity or the other purposes of the sensors, and to integrate that in the panel as well.
Okay.
But in principle, say?
Sorry?
In principle, I wanted to say that I agree with what Ariza is saying, basically, that in principle, you could have used the structural logic, you could have integrated more the two. At the moment, they're very completely.
Yeah.
But I would say the pattern is interesting, and it reminds me of N architecture. Maybe you can look into maybe I can share you a link. It's about the N pattern, how the N's create their underground structure. Yeah, I can share it in the chat.
Do we have any other question or comments? Otherwise, maybe we should conclude the session.
Thank you very much. I will turn off the recording now, right?
Yes.
Yeah, thank you.